Okay, let's look at what resources you have for exam one down here in the modules. And I'm looking at a student view here so that you can see what's going on here. And you can see that exam one study guide is posted first of all. And this study guide is going to say that the following thing, that previous semesters or exams are given to you for review, but I need to change this to summer 2020 exam. The old exams are provided for reference. This page will list the topics that will be covered for this semester. So of course I'm reusing my study guides, and I haven't updated my date there, and I'll do that after this lecture is over here. So you need to go through here and be able to check off each one of these things. Do you understand this? Can you explain all these issues in words? And I'd like for you to be able to do this without referring to your notes. If you can talk a little bit about each one of these issues without referring to your notes, I think that you have a good basis of the material set up. So this would be the first thing I would do. Go through all these issues. Talk about chapter 2. Can you talk a little bit about everything that I have listed here? If there's a word you don't understand, if there's something that you just, I've never seen that before, or I haven't heard it put this way, that's when you need to go back and refer to your notes again, refer to the lectures again, and try to make sure you understand. Again, there is no material from chapter 3 on this first exam, so only the first 2 chapters there, only those first homework assignments here. So the first thing I would do, go through all this, make sure you understand that very, very, very well. When you're done with that, when you think that you're done with that, then the next thing that I would do is I would look at this equation sheet. Now, I would hope that you would have this equation sheet, and this equation sheet would be printed out, and you'd be using it on all of your homework. In fact, what I'm going to be doing after exam 1 is given is I'm going to post the exam 2 equation sheet up on Canvas for you to download, and I would love for you to download that and use that when you do your homework. I think that is very, very important. Okay, so the exam 1 equation sheet, we've been talking about closed systems. It's going to show you the first law of thermodynamics, the change in kinetic energy plus the change in potential energy plus the change in internal energy. This is going to be your stored energy is equal to the transfer of energy into that control volume, the heat transfer and the work. You need to understand the sign convention of heat transfer, that going into a system of heat is positive, going out of a system of heat is negative. For work, inside of this parentheses, you need to know that going into a system from the surroundings is negative, coming out of a system from the system coming out is positive. That's very important. I put this in a little bit easier terms. I just put all the change in energies down here as delta E is equal to summation of Q minus the summation of work. So you may have multiple sources of heat. You maybe have multiple kinds of work. Think about all the kinds of work that you can deal with, okay, and deal with and understand those. In terms of rate now, we're going to say this is going to be the change in energy per time. And we've talked about what happens when this goes to 0. When it's steady state, the energy does not change with time. And we have the heat transfer rate. We have the rate of work, or the power that we're dealing with here. This is how we can work with a problem we're talking about on rate terms. The key words you'll hear here is steady state. That means that this is going to go to 0 as you're trying to figure out what's going on. Now, note that every process has to satisfy the first law. It just has to. So note that you can do that for all the processes. Then I talk a little bit more about work. Now I said work is equal to force times distance, but in this class, we say force is pressure times area. And so there's I do a little bit of a derivation here that maybe is not required, but I want to provide it to you to say that work in this class is going to be the integral of P dV. Okay, and there are many different ways to deal with this work. Remember, if it's constant volume work, I may use the word rigid tank. If it's a rigid tank, that means this is the boundary work. The boundary work is going to be 0. Okay, if it's constant pressure work, okay, now the pressure is going to come out of that integral because all constants will. And now we can say the change in volume and just find out what the constant pressure work is. And remember this thing, if a problem statement does not explicitly tell you that it's anything else, you are going to assume that it's constant pressure work. I will have to say it's polytropic. I'll have to say it's polytropic for you to use a polytropic equation. And so those polytropic equations are provided to us down here below. And look, listen, I've already have constant pressure there. I probably should move constant pressure a little bit above here, because polytropic processes are just these first two processes. P2V2 minus P1V1, 1 minus n. When n is not equal to 0 or 1, you're going to use this equation. Don't have to memorize it. Just use that equation. Now remember what 2 and 1 mean in this. 2 means the final state. 1 means its initial state. So it may be state 1. It may be state 2. It may be state 1 and state 6 that you want to find the work between. It may be state 2 and state 4 that you want the work between. So make sure that you understand that 2 represents final, 1 represents initial. Okay? Same thing goes here. Work can equal, when n is equal to 1, the polytropic exponent is equal to 1. You're not going to see this. PV to the 1 is just PV. PV is equal to constant will be n is equal to 1. And you can solve for the work in either of these two ways. P2V2, natural log of V2 or V1, or P1V1, natural log of V2 or V1. And you should know that you could use either of these because in this case, P2V2 equals constant and P1V1 equals constant. They equal the same constant, so it doesn't matter which one we use in this equation. All right? Now, in these two equations, in fact, in all these equations, I want you to know what would happen if instead of volume, I gave you specific volume. If I gave you specific volume here, you could replace all of the V's, the capital V's for full volume, with lowercase v's or specific volume, but you have to make the added step of taking that times a mass. You have to take it times a mass. So now you're not going to have in this equation pressure times V2 minus V1. You're going to have mass times pressure times little v2 minus little v1. Here you're not going to have P1 capital V1. You're going to have mass times P1 little v1. Okay? Same thing is going to go up here with this top equation. You're going to have mass times P2V2 minus P1V1. And you can take mass outside of that whole equation. So understand how to deal with these if they're specific volumes rather than regular volumes. I've talked about what the rate of power is. It's going to be W dot. It's going to be the rate of work, which is power. And then I have some things here about power by electric shaft, electric motors, power by shaft. What is the power with electric motor? I put in the sign convention there that because it's coming into a system, where shaft is going to be coming out of a system and be positive. This is going to go into a system and be negative. Remember here that W is going to be the angular velocity, and tau is going to be equal to the torque that you're going to have there. W dot here, you're going to have E, that little epsilon there is going to be voltage. I is going to be current that you're going to be dealing with. So make sure you can understand what these things mean, and note that your network is going to be equal to the power from the shaft minus the power from the electric motor. Okay, provide these in here because we haven't dealt with them that much, but I want to provide them so that you can use them on your exam. Now these tables of thermodynamic properties, I left it on here. You don't need it. You're not going to be using that material. That's going to be what was traditionally on my exam ones, but you're not going to be using this on any of your exam problems on Monday night. Okay, moving on. Methods of heat transfer. We talked about 3 methods of heat transfer: conduction, convection, radiation. Note that each one of this gives us a Q dot. It gives us a heat transfer rate, not just heat. It gives us heat transfer rate, and so we have that minus Ka dt dx, and you need to understand that K is going to be your thermal conductivity, and we can look that up in a table in your book, or I'll provide that to you. Area is going to be the surface area, and you must know the surface area for very common items. Rectangles, circles, cylinder surface area, surface area of a sphere. That's what you're going to have to know. Maybe of a cone. You need to know those common surface areas. Okay? Then convection, Q dot is equal to HA, temperature of the surface minus temperature of the fluid. I've made sure that I put all words here so you're not confused with what am I meaning by TS or TF. I've not used the word base here. I've tried to use the word surface because I can write it all out. And then the radiation here, epsilon, sigma, area, T to the 4th minus T to the 4th, okay? And you know this is the only one that you have to have absolute temperatures in. The other two, you can have relative temperatures as well. I gave you what the emissivity. I'm going to have to give you the emissivity in the problem. It's going to be between 0 and 1. And I've given you what sigma is both for both unit systems, for SI and for English systems. We didn't talk much about flux, but flux is going to be the heat transfer per unit area. You actually had a homework problem where they asked you what the flux was, but they didn't say it that directly. They said Q dot, find it at your heat transfer rate per unit area. It's just another way of saying what is my flux. Okay, then we got into thermodynamic cycles. Thermodynamic cycles are a very nice way to talk about problems because now I can deal with multiple processes, but I start and end at the same state. And we went through that lecture and we understand that when you do that, you start and end at the same state, the change in energy is going to be zero, and you're going to end up with the Q net is equal to the work net. And so here I'm using net instead of summation, but it's the same idea. I'm adding up all the heats and I have to add up all the work. So all the summation of all the work has to equal the summation of all the heat. And I can do this also in rate form by putting dots over it. And then I provide you with the power cycle, refrigeration cycle, and heat pump cycle thermal efficiencies or coefficient of performances here, eta, beta, and gamma for you to work with. And so these are for you to reference. And there's 3 different ways to look at it for thermal efficiency, maybe 2 different ways for you to look at it for refrigeration, and 2 different ways for you to look at it for heat pumps. On these problems, I really want you to look at some practice problems and look at the wording, because these equations are really easy to use. However, the wording can really get you going. And so make sure that you understand how to distinguish what I'm trying to ask you for and what the equation needs. Okay, and then finally miscellaneous here. I'm just telling you that if I give you P atmosphere, that's just talking about atmospheric pressure. If I put an A behind a pressure, that's going to be absolute, and denote that everything is going to be absolute pressure unless I say otherwise. And how would I say otherwise? By putting a PG and saying that's a gauge pressure. So then you would have to take that and add atmospheric pressure to it to get the pressure that we would need in our calculations. All thermodynamic calculations need an absolute pressure. And so I've talked to you how to convert between gauge pressure and absolute pressure. The difference here is you're dealing with atmospheres. I told you that if you put a bar over anything, this little square means anything. If you put a bar over anything, I can zoom into that, I guess. I should have zoomed in this a long time ago. If I put a bar over anything, that means it's per unit mole. You shouldn't see anything like that on the first exam. I told you the specific volume was volume per unit mass. I told you the number of moles were the mass over the molecular weight. Okay, this should be a good summary. You should be able to look at everything on this equation sheet and be able to say, oh yeah, I remember that. Oh yeah, I remember that. They should not be things that you're going to have to rapidly think, what was that equation? These should be things that you practice with quite often. Okay? You should be able to talk about these equations and be able to know exactly what that equation is asking for, where it came from, a little bit about where they came from, and not just try to search for this on this equation sheet by, oh, there's an equation, and just try to plug numbers into it. You should be able to understand and be able to explain that to a friend, to your family, to whatever, the mirror that you're talking to as you're getting ready to prepare for this test. Okay, so that is the equation sheet that I would ask you to look at. So first things, study guide and equation sheet. Okay, we get done with that, then I'll go to the next thing that you need to work on.